Good morning, everybody. I hope everybody's doing well. Let me get my palm rejection glove on. And a couple just minor little starting details before we get too far in. Let me share my screen really quickly. Let me bring this over. One thing I wanted to showcase is that we have, where am I? Share. Our exam on Friday. And let me zoom in and put myself in student mode here. So we have an exam on Friday. I hope you've been going through the study guide. If you haven't, it's a bit last minute. So you should already be going through that study guide. And we have a quiz today. So it'll open up at 10 a.m., be open till 9 p.m. Just a single question quiz, no upload needed for section 7.7. Pretty fast and easy. I think that's all I really need to mention. You can see that our calendar looks somewhat sparse right now. It's just because I'm prepping all the chapter 11 material. We'll probably dip our toes into section 11.2 today. We're almost at the end of 11.1. So we will likely dip into series a little bit, not too much though. Other than that, I think I can start in to our lecture. So let me share my desktop screen. Oh, would probably help if I logged in on my laptop here. So let me quickly log in. Okay, it's logging in right now. Just grab my stuff. Otherwise, you wouldn't be able to see what I'm writing. That wouldn't be fun. There we go. Oh.
This meeting is being recorded.
Ignore that. Sorry about that. That's because I had my microphone on and the audio on my laptop at this very same time. I apologize for that. All right. So hopefully there's no echoing anymore. Let me go ahead and share my screen. I'm allowed to do that once a semester, I guess. And here we go. So remember last time we were going through this material right here. We were just in the middle of dealing with sequences. And today, like I said, we'll probably dip our toes into series. Let me turn off the doorbell when people log in. That way I don't have to hear that. Excuse me. And now we're going to go ahead and do one last example before we get into some deeper theory of sequences and then immediately jump over to series. So this last example is a very good example. We didn't have time to do it in last class session. But now, beginning of this class session, we totally have time to do this. So determine whether the sequence converges or diverges. Just to remind you, a sequence of values converges if its limit as n goes to infinity becomes finite. So that's just a good reminder. If the limit as n tends to infinity of your sequence values, if that becomes finite, I'll just call that finite, then we know it converges. If it does not become finite, then we would say that it diverges. There's two ways to not become finite. That's why I'm not saying if it becomes infinite, it diverges. There are two ways to not become finite. Either one, it goes to infinity or negative infinity, or two, it does not converge to either infinity or negative infinity, nor does it converge to a finite number. So in other words, it could be bouncing around like between 1 and -1 or something like that. We would also consider that to be a divergent sequence. So it's much easier to define it in terms of convergence, because we can just say, well, if it becomes a finite number, it converges. Otherwise, it diverges. That's a really nice, clean definition. So let's go ahead and deal with this guy. Let's see if it converges or diverges. And the way we'll do this is just take the limit. We're back to Calc 1. So take the limit as n goes to infinity. of a sub n, and that would be n squared times the quantity 1 minus the cosine of 2.5 over n. So as n tends to infinity, you have a product of two sequences here. The first one, which I'll do in red here, that guy will tend to infinity. The second one, which I'll just keep in black there, that tends to, as n tends to infinity, well, as n goes to infinity, this, I'll highlight it, this argument of the cosine will tend to 0. And that means that that cosine is tending to the cosine of 0, which is tending to 1. And therefore, 1 minus that is tending to 0 itself. And so we have something like 0 times infinity. However, as I mentioned last class, and as your Calc 1 instructor should have mentioned to you, in calculus, the quote unquote 0 times anything is 0 is not true. This is not 0 times infinity. This is something approaching 0 times something approaching infinity. This could be finite. This could be 0. This could be infinite. We don't know. So we have to use laws of limits to evaluate this. So let's go ahead and this is also called an indeterminate form, 0 times infinity. However, you cannot use L'Hopital's rule on it because, well, it's not of the form infinity over infinity or 0 over 0. So you have to kind of transform this a little bit. Also, we're going to engage one of the theorems we wrote down last time. And let me see if I can quickly find that. It's probably at the top of this list here. Maybe it's this one. Nope. Maybe it's that one. Yes. So we're going to engage with this theorem right here, which just tells us that if we're investigating a sequence, and if we can write it as a function instead, then if the limit as x goes to infinity of the function converges to some finite number, then the sequence will converge to that same finite number. Again, as I mentioned last class, the converse of this theorem is not true. Just because a sequence converges does not mean its function converges. But in this case, we get to go ahead and let me hop back here to page 14, I think is what it was on. In this case, we're going to trade out the sequence for its functional alternative. It's just much cleaner to work with. So I'm going to say, let's take a look at or consider the limit as x goes to infinity. There's a few reasons why you have to trade this out for a function of x. One major reason is if you have an indeterminate form like we have right now, you likely will have to use L'Hopital's rule. And L'Hopital's rule, eventually, and L'Hopital's rule can only be used on differentiable functions. Well, a sequence is not differentiable because it's just a bunch of discrete points. They don't have derivatives. So you need a nice smooth function to have a derivative. So you have to trade it out for a continuous variable x, not a discrete variable n. I know most people look at that and just think, well, it's just notation, whatever. And it is kind of true. I do agree with that. But theoretically, the mindset is still very important. There is a significant difference between these values of n for a sequence because they're just 1, 2, 3, 4, and 5. They're just discrete points versus the values of x here, which are non-discrete points. They actually are continuous. It continuously flows from 1 through all the way up to infinity. So it includes pi and root 2 and 100 root 2 and all that fun stuff. Okay. So anyhow, it still is infinity times 0 here. So we're going to have to do some mathemagic here. So let's go ahead and rewrite this as the limit as x goes to infinity. I'm just doing some algebra before I do my calculus. And I know what I want to do. I want to get this to be L'Hopital's ready so I can use L'Hopital's rule on it. So I'm going to go ahead and leave the 1 minus the cosine of 2.5 over x. I'll leave that in the numerator. And I am going to write the x squared as a 1 over x squared, because that's what x squared is. It's a little bit cleaner to write it that way for L'Hopital's rule. So if I write the x squared that way, my denominator will be a 1 over x squared. So those two are identical statements. But now, as x goes to infinity, instead of being infinity times 0, you have the numerator, which is approaching 0 still. Let's say this whole thing is approaching 0. And the denominator is also approaching 0. So this is L'Hopital's ready. 0 over 0 means I can run L'Hopital's rule on it. So let's go ahead and do that. This equals, and if you're from my calculus class, you know that I like to justify or tell people what rule I'm using. So this equals via L'Hopital's rule, the limit as x tends to infinity of. L'Hopital's rule just says the value of this limit, if it exists, is equal to the limit as x goes to infinity of the derivative of the numerator divided by the derivative of the denominator. It's basically what we would love the quotient rule to be, but it's not the quotient rule. So let's see, the derivative of the numerator, derivative of 1 is 0. Derivative of a negative cosine is actually a positive sign of that 2.5 over x. But then by the chain rule, take the derivative of that 2.5 over x. Well, that's going to be a negative 2.5 over x squared. In the denominator, taking the derivative of a 1 over x, that'll be a negative 2 over x cubed. All right. Now, at this point, before I go to evaluate this, I suppose I could try to evaluate this, but it won't be fun because you can see it's still going to be 0 over 0. But before I go and try to do that, I'm going to do some algebra just to clean this up. So let's multiply both numerator and denominator, first of all, by the negatives, just to make those negatives go away. Also, I'm going to multiply both top and bottom by x cubed. So a little bit of algebra here. It's kind of interesting when you do calculus, because if you were to enumerate or tell yourself every single time you're doing algebra, let's say I just put an A there for the fact that I'm using algebra or arithmetic, whichever, you'll find out that most of calculus is actually algebra and arithmetic. So anyhow, also, you know what I'm going to do? I'm going to pull that 2.5 and that 2 out front as well. So 2.5 in the numerator and a 2 in the denominator. I'll move those out front just because I can. And let's see, I'll get an x sine of 2.5 over x. Again, I multiplied numerator and denominator by x cubed. So that's what it kind of compresses down to. So I did some algebra there. Now I'll take a look at this. I say, okay, let's see what happens if x goes to infinity. Well, if x goes to infinity, then obviously this tends to infinity. As x goes to infinity, the argument of the sign is actually tending to 0, which means the sign itself is also tending to 0, because again, sine of 0 is 0. So again, we still have infinity times 0. So you may think, oh, L'Hopital's rule is broken, it won't work here, but it actually can still work. You just have to remember that L'Hopital's rule requires multiple L'Hopital's rules sometimes. So let's go ahead and do L'Hopital's rule again. And before I do, I'm going to put a little A up there, meaning that I did algebra in that step. So this is equal to, I'm going to do a little bit more algebra. This is a 2.5 over 2 still. I have a limit as x tends to infinity. The reason why I'm doing the algebra right now is, no, you can't use by parts because we're not integrating. We're just taking a limit. So the reason why I'm going ahead and doing some algebra here is because I want to use L'Hopital's rule. I can't use L'Hopital's rule when it's infinity times 0. So the way I'm doing this here, I'm saying the sine of 2.5 over x divided by 1 over x. So x is the same as 1 over 1 over x. And so there we go. We have rewritten it like this via some algebra. And notice that numerator is going to tend to 0 because, again, as x goes to infinity, 2.5 over x is tending to 0, sine of 0 is 0. And that denominator also is tending to 0. So this is ready for L'Hopital's rule one last time, I promise. Actually, I don't know if I should promise that. Yeah, I promise. So this is equal to, via L'Hopital's rule, I'll just leave this 2.5 out front and this 2 here. The limit as x tends to infinity, the derivative of the sine is going to be the cosine. And then by the chain rule, the derivative of its argument, 2.5 over x, is going to be a negative 2.5 over x squared. In the denominator, the derivative of 1 over x is a negative 1 over x squared. This is very nice, actually. Now doing a little bit of algebra. I'm going to move, first of all, you get to cancel those negatives. I'll move the other 2.5 out. So I have a 2.5 squared hanging out front now. And we have this limit as x tends to infinity. And you can see if I multiply both numerator and denominator of this expression by x squared, those will disappear and you'll be left with just a simple cosine of 2.5 over x. And as x tends to infinity, well, 2.5 over x will tend to 0. And we happen to know the cosine of 0 is 1. So this via, it's not technically direct substitution, so I'm not going to write direct substitution, but via evaluation of this, as x goes to infinity, again, 2.5 over that x is going to tend to 0. Cosine of 0 tends to 1. And therefore, you have 1 times 2.5 squared, which is 6.25 over 2. I can do the 6.25. I just can't do it. It's 3.125, I think. There we go. Perfect. So there we go. Notice, I know it's kind of weird because Virginia just had asked by parts. We had been working with integration this entire time, and all of a sudden we switched gears, and it's almost like we went back into first gear, and we're back to just looking at limits, the very beginning of calculus. There's no integration yet. Integration comes back involved a little bit later on. So we're going to take this longer aside before we get back into integration. All right. So it's a good reminder of L'Hopital's rule and how to work with it and all that fun stuff. So if you do have questions, let me know. I'm going to take a sip of my chai. All right. Now, the downhill slide out of this section is all about bounding sequences. And you can see this beefy definition here. It's got a lot of information in it. So there's a question. Would we need to make a formal statement at this point that, oh yeah, thank you. Yeah, you do want to, yeah, it's true. Generally, I know what you mean when you get down to here and you say, oh, the limit is 3.125. By virtue of it being finite means it converges. But yeah, formally, you probably want to say thus. So this implies A sub n converges. Thank you very much for reminding me. That's good. To 3.125. That is kind of important because you're dealing with the sequence. No, thank you. You're dealing with the sequence, and often you get lost in the details of what you're doing that you forget why you're doing it. But the reality is we did that limit because we're trying to figure out, does that related sequence converge? Now, remember, we traded out the sequence for its related function, and the related function converges to 3.125, but we had that earlier theorem that tells us if the related function converges to some finite value, then the sequence converges to that same finite value. So thus, our sequence converges to 3.125. The punchline is, whenever you're dealing with a sequence, you could trade it out for its related function and see if you can get the limit of that function to converge. If it does, whatever it converges to, the sequence converges to that as well. Now back to this beefy old definition that we need all this information to help us bound sequences. Sometimes it's just more important to know that a sequence is bounded than to know what it tends to. And you'll find that's going to be a theme for this actually the rest of mathematics, is that it's more important to know that you can get an answer than what the answer is. We often are just concerned, is this a solvable situation? Is it possible that that you can make $1 billion and be the happiest person on earth? It's possibly possible. That's a solvable problem, maybe. Who knows? I hear money, that much money brings its own little headaches, though. So anyhow, I'd welcome a headache like that every once in a while. I'd be okay with that. Definition here. Let's go through this piece by piece. There's a lot going on. So given any sequence that I hand you, any sequence, we can have the following defined. We could say that the sequence is increasing for a sequence or a series of values. I don't want to use those words. I don't want to use sequence or series. In fact, I have to put my phone away when I start this conversation, because I didn't have to do that until last year, because I didn't have an iPhone until last year. I had Android, but once I got an iPhone and I was teaching and I kept saying sequences and series, my phone would pop up and ask me questions. So we say that a sequence is increasing for values k plus 1, k plus 2, all the way to some value, right? So it could be k equals 10, 11, 12, ... all the way up to 72. Okay. So look, over that interval right there, we would say that a sequence is increasing if the next term in the sequence is always greater than the previous term. Now, that seems like a very easy definition, and it should be. If your next term in line is greater than the previous term, yes, it's increasing on that set of values. Okay. So that shouldn't be mind-blowing or anything like that. Let's see, what else do I say there? For all n in that sequence. So we say it's increasing for these values. Okay. A similar definition exists for decreasing, by the way. However, it could be the case that you have a sequence that is increasing for a bit and then starts decreasing for a bit. So it's increasing for certain values of n and decreasing for other values of n. What would be nice is if we had a definition of what would we call a sequence if it's always increasing. So what would it be if we had this sequence right here and it was increasing forever and ever and ever and ever and ever, never decreasing, just always increasing? Well, we have a word for that. If our sequence is strictly increasing or decreasing for all values of n, then we would call the sequence monotonic. So it's monotonically increasing. In fact, here's my sequence of dots there. This is monotonically increasing. And of course, we have a similar statement for monotonically decreasing. If your sequence is always decreasing, we just say it's monotonically decreasing. Monotone, right? It's just one behavior. It's kind of a good way to think about that. So those two definitions, again, they shouldn't blow your mind. There's nothing really crazy about these definitions. It's just wording that we need to all agree upon so that I don't all of a sudden out of left field say, oh, and this sequence is monotonically decreasing. And you say, what the heck is that? So we have that language in our nomenclature. Now we go on to the third part of this. If there exists some number little m such that our sequence values are always greater than or equal to that little m, then we say the sequence is bounded below. and its lower bound is little m. If you look at this monotonically increasing sequence here, let's just pretend as though this value is 1, 2, and right, these are the input values, the n values. Okay. Let's pretend that this output level right there is output of a 0.5. Let's just say. Notice because it's monotonically increasing, the lowest value that this sequence ever takes on is a 0.5. So I would say that this sequence has a lower bound of 0.5. Let me actually write that down. This sequence has a lower bound of 0.5. However, I just want to let you know that there's actually an infinite number of lower bounds for this sequence. 0 is also below all values of this sequence. So 0 is also a lower bound. -10 is also below all values of this sequence. So -10 is also a lower bound. So there's technically an infinite number of lower bounds, but then you don't need to know this part. I'm just going to say it out loud. I'm not going to write it down. There is a greatest lower bound, and the greatest lower bound for the sequence is 0.5. It's the greatest number that still makes it a lower bound. Don't worry about that. Nobody in this course or at this level is really that concerned about that. All we care about is that, can you say that this sequence has a lower bound? The answer is yeah, it has a lower bound. It's 0.5 or 0 if you want to use that. It doesn't really matter. Okay. Likewise, oh, by the way, I did say that this number is called the lower bound. I'll highlight that. And there's a similar definition for upper bounds. So that is if your sequence is always below a number. So let's just pretend that our monotonically increasing sequence, it still increases, but it ends up slowing its increase down, and it's always below a height of, let's say, 27. Then we'd say, oh, there's an upper bound of 27. So it's bounded above by 27 and bounded below by 0.5. And finally, if the sequence is both bounded above and below, then we would just use the word bounded, not bounded above, not bounded below, but we'd say, hey, I have a bounded sequence, which just basically means it has a floor and a ceiling. That's what a bounded sequence is. It's got a floor and a ceiling. And bounded sequences are very powerful. If you have a monotonically increasing bounded sequence, there's a theorem that we're about to be introduced to that tells us that sequence will converge. All I need are borders and knowing that it has a monotonic behavior, and I'm golden. I know that I have a convergence. All right. So let's go ahead and, oh yeah, sorry. Let me read this warning. Despite what the author or your tutor says, it's advisable to use calculus techniques when determining whether a sequence increases or decreases. The author is going to tell you something different, but it's better to practice your calculus. So to determine whether a sequence is increasing or decreasing, change it into its related function and take the derivative. If the derivative is always positive, then your function's increasing, therefore your sequence is increasing. If the derivative is negative, then your function's decreasing and your derivative is or your sequence is decreasing. So use derivatives in general to determine whether a sequence is increasing or decreasing. Trust me, it saves you a lot of headache. Just giving you that heads up. All right. Let's see what we do here. And I'm not going to do the proof on this. I thought about doing the proof, but the proof is a little bit tough to do, and I just don't think that it would benefit us to go through it. It's kind of a beefy proof. If we do have time, I'll go back through and possibly do it. I'm not 100% sure. So this is what I was just mentioning though. If you have a monotonic, which means it's either always increasing or it's always decreasing, so you have a monotonic sequence and you know it's bounded, then the sequence has to converge. Now, I'm not going to prove it. Instead, I'll give you a justification, just a visual justification. So let's say we have a ceiling to our sequence values and a floor to our sequence values. And I don't care what you want. If you want it to be decreasing, then I'll go with that. Let's suppose that we have a decreasing sequence, monotonically decreasing, by the way. Now, because it's bounded, that means it's bounded both above and below, which means that it will eventually have to slow its decrease. We have the condition, we've said it's decreasing, which means every term in that sequence will be lower than the previous term. But because I've also said it's bounded, well, that rate of decrease is going to have to slow down. Actually, let me make these dots a little bit easier to work with so that I can kind of glue them together here. Let me do this. Trying to get down to this as quick as possible so that I can, there we go. All right. So they still get lower and lower. It's just that they slow their decrease, but it'll still decrease. But because it's bounded below, it's going to, that rate of decrease is going to slow down quite a bit. And you can see that it's going to have to converge. It'll have to eventually become something finite because it's bounded. So there's a good, not proof, but visual justification as to why a bounded monotonic sequence will be convergent. If you say, but what if it hops up here? Then I would say you've broken the rule that it's monotonic, right? So the next dot has to be slightly below the previous dot, and so on and so forth down the line. And my little warning here, the converse is not true. That is, just because you have a convergent sequence does not mean it's bounded, and it does not mean it's monotonic. Okay. Actually, technically, it would be bounded. Convergent sequences are bounded, but it's not necessarily monotonic. And if you want to see why, so let me give that in red. Why is the converse not true? In other words, why is it that if I have a convergent sequence, why can't I say it's monotonic and bounded? Well, it's the monotonicity that is the issue. So suppose the sequence A sub n converges. Well, then there's some value. Get my ruler out. There's some value that our sequence tends to because we said it converges. So here's a dot, here's a dot. And right now, how I'm drawing it, it looks like it's monotonic. But then let's suppose it does this. This sequence converges to that line, whatever that line is. Okay, but notice it's not monotonic. So just because I have a convergent sequence does not mean it has to be monotonic. So that's a good visual as to why the converse of that theorem is not true. You do not have to have a monotonic, a sequence being monotonic to be convergent. However, monotonic and bounded definitely implies convergence. Let's take a look at how you would use this. This is how can I say this? This is a nice general way to say, to showcase that you have a convergent sequence without actually having to go through showing what it converges to. It's a really nice theorem. So let's take a look at a few examples. Determine whether the sequence is increasing, decreasing, or not monotonic. And when I say increasing or decreasing, honestly, I really mean, is it increasing monotonically or decreasing monotonically, or is it just not monotonic? So let me just say monotonically, and most of us use MT for monotonically. So is it increasing monotonically or decreasing monotonically? You say a word enough and it starts sounding like it's not a word anymore. Monotonically does not sound like a word anymore to me. All right. So To determine, and it should be somewhat obvious to you that the sequence is going to be decreasing, but to determine that it's decreasing, let me show you the method. So method, or how to. All right, how to. Given a sequence, a sub n, determine if it's monotonic. I'll just put MT. So how do you do that? Well, the first thing you do, exchange a sub n for f of x, where f of n is equal to a sub n. So we're trading out for its related function of x. Second thing you're going to do is compute f prime, right? And then third thing, if f prime is less than 0 for all x in the interval in question, so in domain of sequence, then a sub n is monotonically decreasing. If f prime is greater than 0, then obviously a sub n is monotonically increasing. What is going on? Let me send a text. Hold on a second. There we go. All right. So that's the basic idea of it. Actually pretty easy. So let's go ahead and do it here. I'm going to trade out that sequence for its related function. So we're going to let f of x equal a negative x squared. I totally get, by the way, that this is very, very easy to see. It's just simple. It's an upside down parabola. So yes, I totally get it's decreasing from 0 to infinity. But I'm showing you the general idea. So once we hit harder examples, we can apply the same method to those harder examples. F prime of x is equal to a negative 2x, which is less than 0 for all x greater than or equal to 0. I should say it's less than or equal to 0 for all x greater than or equal to 0. And we are concerned with x greater than or equal to 0 because that's the domain of our sequence. So this implies that a sub n, our sequence, is monotonically decreasing. The author will have you look at a sub n, compared to a sub n plus 1 and say, well, if a sub n plus 1 is less than a sub n, then you know it's decreasing. The problem is that works for very easy functions or easy sequences, but does not work for very difficult sequences, whereas taking the derivative works. So I like to teach things that work always. I don't like to teach something that works sometimes. All right. So since we now know that the sequence is monotonically decreasing, I'll just wrap that up right there. We now need to ask ourselves, is it bounded? Now, remember, to be bounded, it has to have a ceiling and a floor. We do know, because it's monotonically decreasing, sequences are very interesting like this, that when you know something's, for example, in this case, decreasing, its initial value is the greatest value it will ever be. So a sub 0, because our sequence starts at 0, a sub 0 is going to be the largest value for this sequence. So I'm going to say a sub n is bounded above. It's not bounded below, but it's bounded above by a sub 0, which is 0. Just looking at the sequence, because it's decreasing, right? So it should make sense. If something's falling, the highest value you'll ever have is the very first value. However, a sub n is not bounded below because it's always decreasing, and you can easily see just from the sequence itself as n goes to infinity. So I'll even say that the limit, but the limit as n goes to infinity of a sub n, which is equal to the limit as n goes to infinity of negative n squared, is equal to negative infinity, which is not finite. So this implies no lower bound. If you say, well, negative a billion is the lower bound, I would say, no, there's a value I can plug in to get below negative a billion. So there we go. So this sequence is not bounded. A sub n is not bounded. And we often use BDD for bounded. That's not just me. That's in the mathematics community. We just love to shorthand. BDD is bounded. So there's a good first example of playing with the monotonicity, or determining whether a function or a sequence is monotonically increasing or monotonically decreasing, and whether or not it is bounded. So far, are there any questions on that? I'll pause while I take a drink. And I'm back. All right. Well, I'll keep my eye on the chat. If you do have questions, I'll hop back. This is kind of an interesting problem. This is one where you cannot exchange it for a function. You wouldn't know it if you've never done Calc 2, or maybe you would actually. Maybe it's somewhat obvious to you that you would not trade this out for a function. But determine whether the sequence is increasing, decreasing, or not monotonic at all. And no matter what, is it bounded? Well, this one, if you try to trade it out for the function version, it would be a -1 to the x plus 1. But there's a problem with that. X is a continuous variable, which means x could be a half. And if x were a half, you'd have a half plus 1, or 3 halves. -1 to the 3 halves, you're taking the square root of a -1 and then cubing it. And square root of -1 is not a real number. So trading this out for x's is not going to work. Let me go ahead and say that again. Because x could be, let's just say 1/2, we would be taking the square root of a negative number. This is a no-no. So we can't do that. So trading this out for the function is going to be a bad idea here. You won't be able to differentiate or anything like that because you can't differentiate over the complex numbers right now. So what do? Well, probably the best thing to do is just write out what the sequence looks like. So I'll grab the sequence and I'll say this is equal to, well, when n equals 1, I have -1 squared. When n equals 2, I have -1 cubed. When n equals 3, I have -1 to the 4th. When n equals 4, I have a -1 to the 5th, and so on and so forth down the line. It just alternates between 1 and -1 forever and ever and ever. You can see that's popping. It's basically dropping, rising, dropping, rising, dropping, rising. So this is neither increasing nor is it decreasing. This is definitely not monotonic. There's no need to explain that because it's very obvious. It just pops between 1 and -1. However, it is bounded. This is a bounded sequence. there is a value that's always less than or equal to all the values in the sequence, and there are values that are always greater than or equal to all the values in the sequence. So one option is to say, well, it is definitely bounded. I'll just say that first. And then parentheses, I'll just say bounded below by -1 and above by +1. Now, those aren't the only bounds. You could say it's bounded below by -10 and +10. It is true. It is bounded below by -10 and bounded above by +10. That is absolutely true. So you don't have to choose the tightest bound. You just have to have a bound. So in this case, it is bounded. So which values you choose is your choice. I tend to try to choose the tightest bounds, but nobody's really going to force you at this level to find the tightest bounds for the sequence. Well, this is kind of a gimme example, but I just want to make sure that I didn't lose anybody in this part. So let me know if there's anything in here that you're just like, what just happened? Then we can talk about it. Okay, I'll hop forward. Oops. Yeah, a page. Now we're getting into the stuff where I really do believe that the calculus part's kind of important. So determine whether the sequence is monotonically increasing or decreasing, and determine if it's bounded. In this case, I'm going to go to my how-to on this, and I'm just going to exchange this out for a function. I'm going to let f of x equal x over x plus 1. And then I will take the derivative of f. This is going to be the quotient rule. So the derivative of the numerator is 1 times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. Cleaning that up using some algebra. We have x minus x upstairs. We have 1 over x plus 1 and quantity squared. That numerator is positive. That denominator is always positive. So therefore, that fraction is always positive, which means the derivative is always positive, which means the function is always increasing. Which means our sequence is increasing. In fact, it's monotonically increasing because it's always greater than 0, the derivative is. So it's a very fast way to determine whether a sequence is monotonically increasing or decreasing. Again, if you read the text, the way the author does it is just too convoluted and only works half the time, if not less than half the time. So it's much easier to just take derivative. Let's see. So it's monotonically increasing. Great. We have that. Let's see if it's bounded. So first of all, if you know a a sequence is monotonic, its very first value is either the lower bound or the upper bound. In this case, it's monotonically increasing. So our sequence probably looks like this. So I know let me draw a few more dots there. So I know the very first value is its lower bound. So the lower bound, I should say the first value is one of its lower bounds, right? There's an infinite number of lower bounds, but it's kind of easy to find the very first lower bound here. Let n equal 1. So the lower bound is 1/2. So I know the lowest value the sequence will ever be is 1/2. Now let's see what happens if you take the limit as n goes to infinity. Let's see if we can find an upper bound for this. Now, in this case, I do kind of hand wave a little bit. So I generally would tell students, trade things out for functions, like switch everything to x's. You could do that. It's totally fine. There's nothing wrong with that. But sometimes when something's this easy, there's no need to switch it out for x's. We know this limit's going to be 1. That's a very easy limit to compute without me doing any type of L'Hopital's. So if I'm not touching L'Hopital's, I generally don't trade out for X's. I leave it in terms of N's, but I just went ahead and traded out for X's. So I know an upper bound. So is an upper bound. Now, I didn't actually have to compute that limit. I could have just said, listen, do you see the numerator is always less than the denominator? And you would say, sure. And then say, great. That fraction, whatever it is always less than 1. And you would say, yeah. I say, okay. So it has an upper bound. It has an upper bound, it has a lower bound, and it's monotonically increasing. Again, it has a lower bound, it has an upper bound, and it's monotonically increasing. And what that tells me, without even knowing what the bounds are, that tells me that the sequence converges. Because again, it's bounded and it's monotonic. And it's there's a question in the chat about getting a clarification. So do I have to always let me try to reword it slightly. So the bounds are any numbers less than n just for, okay, so the bound, so for example, a lower bound here, since I know that this sequence is increasing, a lower bound is the very first term of the sequence. However, I don't have to use that. I could have said a lower bound is 0. It's any number less than or equal to that very first value. As long as I know there is a bottom floor and a ceiling, then I know it's bounded. I don't have to actually strictly say the strictest lower bound is 1/2. I don't have to. Nobody's going to ask you to do that. They shouldn't, at least. Okay. So I hope that answers your question. I think that did, but yeah, you don't have to normally state the strictest. Most people are going to, though. I think most people are going to say, well, it's increasing forever, so the lowest value it'll ever have is the very first one. But you could say 0, and you could say the upper bound is 1,000, because that is technically an upper bound for 1,000. It'll never get there. So the main part is it's bounded, and it's monotonically increasing. So because of that, I know it converges. Pretty good stuff. All right. The last example I have in this section is just about sequences. So we did not, how do we prove the bound? Hong's asking, how did we prove the bound that we got? So if they ask for the bound, then you would prove it this way. Just take the limit as x goes to infinity. Right? So as x, we know it's monotonically increasing. So as x goes to infinity, that upper bound is going to be that 1, because it's monotonically increasing to get to that. It'll never actually reach 1, by the way, right? Because the numerator is always less than the denominator. So this fraction is always less than 1. It's approaching a value 1, but it's always less than 1. But that's how you actually do it. Okay. And the last example in this section, it says use technology to show the first 10 terms of this sequence. Now I didn't pre-do this, so let me just prep it a little bit. I'm going to go over to Google here and okay, there we go. And I'm going to go here. All right, I'm ready. So I'll show you how to use Desmos to, actually somebody else is going to show you because they wrote the script for it, but it's very quick and easy. I'm going to show you what they did and how we're going to apply this to our situation. So share screen. Yes. And I want to share this bad boy right here. Share. Okay. So this is I hope that you all can see that. I think you can. This is Desmos. I'm not logged in. Oh, well. All I did was Google Desmos sequences just so that I can get a view of this. Notice the way that this is done is that in Desmos, you set up a number of terms for your sequence. This person chose the capital N for that. Perfectly fine. You could change that to whatever letter you want. And then you create your sequence A of, normally we'd say A sub n, right? Well, unfortunately, Desmos will not work with little n's. So you have to create your function as a function of x. Now, our function of x that we're considering in this situation is actually x cubed over x to the fourth and then plus 10,000. Okay, that's our sequence. It was supposed to be a sub n is equal to n cubed over n to the fourth plus 10,000. But again, it's not. We had to do it with x's for Desmos. And then we wanted to plot these points. And the way we plot these points is we plot the points n, comma, a of n. And our n values are going from 1 all the way up to capital N. Sounds confusing, doesn't it? It is a little confusing. That's why if you just Google Desmos sequences, it'll bring this one up, and then you can fill in whatever you need. Now, here are the first 10 values of this sequence. Does this sequence appear to be monotonically increasing or decreasing? You're probably looking at that and you say, yeah, it looks to be monotonically increasing. I would agree. Totally does. If we go to the 11th, the 12th, the 13th term, it still looks like it's increasing. So let's go ahead and figure out if it is increasing forever or not. And you don't want to use Desmos to always showcase that because you won't have Desmos to showcase that normally. So how would you showcase that theoretically? Let me go over to my laptop, share screen. Yes. There we go. And share. Let's go ahead and prove this. All right. Does it actually, so does the sequence look like it converges? Yes, it does look like it converges. Does it actually converge? Well, to determine if it actually converges, because it looks like it was bounded and it looks like it was monotonic, right? It looked like it was monotonically increasing, kind of like this. And it looked like it was slowing down. So it looked like it was bounded below by 0, maybe bounded above by, I'm just looking over, maybe a 0.06 or something like that. Okay. So it definitely looks like it was going to converge. Let's go ahead and prove that it does or find out that it doesn't. We're going to let f of x equal the function version of this sequence, which would be x cubed divided by x to the fourth plus 10,000. Let's see if that's right. Yeah. And we'll take the derivative. We just want to know, is the derivative always positive, right? Excuse me. So let's go ahead and use quotient rule. Derivative of the numerator is 3x squared times the denominator of x to the fourth plus 10,000 minus the numerator, x cubed, times the derivative of the denominator, 4x cubed, all over that denominator squared. There we go. And let's go ahead and clean up the stuff using some algebra. So I have 3x squared times x to the fourth, which is going to be a 3x to the sixth. We're going to lose a 4x to the sixth. So we'll have a negative x to the sixth. And then we'll have a plus 30,000 x squared. Okay. And that's all over some positive number. And that's kind of critical to note there. That denominator is always positive. It's not even ever 0. It's always positive. So that's going to be very helpful. Let's see. So this is equal to, via some more algebra, I'm going to go ahead and factor out a negative x squared out of that numerator. So I'm left with x to the fourth minus 30,000. There we go. The problem here is we don't know if that numerator is always going to be positive or always going to be negative. So we need to go ahead and plot some numbers on a number line and find out. Let's see, we're doing this problem for n from 0 to infinity. So let's go ahead and draw a number line, start at 0. Notice that's where x squared turns into 0. This x to the fourth minus 30,000, that turns into 0 at the fourth root of 30,000. So I'll mark that right here, the fourth root of 30,000. That's just via some algebra there. And then you make a sign. Well, I guess we're already doing it. We're making a sign chart, right? If you plug in any value between 0 and fourth root of 30,000 into that numerator, so let's just plug in a 1. At x equals 1, our fraction is some positive value in the denominator. And in the numerator, we have some negative value times 1 minus 30,000, which is another negative value. And so we have positive over positive. So we know our function is increasing on the interval because we're looking at the derivative, right? So our function's increasing. But then if you go beyond the fourth root of 30,000, a pretty easy number to plug in that's greater than the fourth root of 30,000 is 30,000. That's greater than the fourth root of 30,000. Trust me. So if that's the case, let's see, the numerator has a negative number times 30,000 to the fourth minus 30,000, which is going to be positive, over a positive, and that will be a negative value altogether, which means your function's decreasing from that point forward. This is kind of the interesting thing about dealing with technology, is that with technology, you could fool yourself into thinking that you have a monotonically increasing sequence and that it's bounded, but in reality, it's not monotonically increasing. Our sequence increases up to a certain number and then starts to decrease. So did we label that sequence? No, we did not. So I'll just say a sub n. I'll just call it a sub n, even though we didn't actually label it earlier. Say a sub n is not monotonic. Because again, it's increasing for a little bit, but then it starts decreasing as time goes on. And let's see. Nope. But it does say, does it actually converge? So does it look like this, the sequence converges, and then does it actually converge? So we cannot use, right now, it doesn't seem as though we can use the theorem that we mentioned earlier, which I will scroll back to. This one right here. Yeah. This theorem says that if we have a sequence, it's monotonic and bounded, then the sequence must converge. And so you look at this last problem and you say, shoot, I can't use that because it's not monotonic. Oh, that sucks, right? Because you had an increasing sequence for a while, and then our derivative tells us it's going to start decreasing, right? So we think, I guess that theorem can't be used. But here's the coolest thing about sequences, is that the first billion values of a sequence are just finite values. You could throw them out if you want. If you want to know if a sequence converges or diverges or something like that, and you can't show that it's monotonic initially, but you know that later on it does obtain the monotonic property. So later on, specifically after the fourth root of 30,000, our sequence then becomes a monotonically decreasing sequence from that point forward. Well, if I'm trying to figure out if a sequence converges, I don't care about the first 10,000 terms. All I care about is what are the infinite number of terms after that tending to. So I'm going to write this down to be very clear about this. Initially, I have to zoom in to make my handwriting look nicer. Initially, it looks like we cannot use monotonicity I don't know if that's how you spell that, by the way. Uh, and bounds to show A sub n converges. This is because A sub n is not monotonic. However, if you throw out the first chunk of terms, let me spell that better. Convergence is only about considering the last, in quotes, chunk of terms in a sequence. We can always throw out the first million terms. That's an example. I'm not saying that you always throw out a million terms. I'm just saying you could always throw out the first group of terms and then consider your sequence from that point forward. Note our sequence that we have will actually start to monotonically decrease at a certain point. So since A sub n is monotonically decreasing for all n greater than the fourth root of 30,000. Well, one, we know that we have an upper bound, right? We have an upper bound to our sequence because it was increasing, and then at some value, it turns. At that value, wherever it turns, that's the upper bound or an upper bound. And so what you could do is you could find out what the fourth root of 30,000 is. And I have a calculator around here somewhere, I'm sure. Not that every good mathematician should, but 2, 3 raised to the 0.25. So that's around 13. That's what the fourth root of 30,000 is, roughly around 13. So what I'm going to do is just see what 13 is if I plug this in here. And the way I'm going to do that is I'll probably just go over to Desmos just to click on it. So let me give me a moment. I'm not going to abuse you guys with it. So that's if you were to plug in 13 or even 14, just to be careful, 13 or 14, so 0.05697 or 0.05668. So I'm just going to go ahead and just say, I know because it has that turning point at the fourth root of 30,000. I know that the sequence is going to be bounded above by the value around there. And the value around there is like 5/100ths. So I'm going to say it's bounded above by 1. Since A sub n is monotonically decreasing for all n greater than the fourth root of 30,000, we can say A sub n is bounded above by 1. And I'll just put this in parentheses because 1 is much greater than A sub 13 or A sub 14, which are the fourth roots of 30,000. The fourth root of 30,000 is between 13 and 14. So I'm just picking those two values as my turning point. Now let's see if we can find a lower bound. Well, let's not even find the lower bound. Let's just take a look at the sequence. What's one thing you know about that sequence for all values of n? No matter what I plug in, what's something you could say about that sequence? Denominator is greater than numerator. It's true. But what can you say about the sign of that sequence? It's always positive. Yeah, it's always positive. So I know that sequence is always positive, so I know the lower bound is 0. So it has an upper bound, bounded above by 1, and a sub n is always greater than 0, so bounded below by 0 implies it converges. Again, because we have, let me highlight it, bound above and below, so it's bounded, and it's monotonically decreasing. Thus, it converges. I don't know what it converges to, and I don't care, but it actually converges to 0. But the reality is that often you don't care what it converges to. You just care that it converges. I want to know if I did this operation forever, would eventually converge to something. If you say yes, then I'll start doing that operation forever, right? And just to showcase, hopping over to Desmos really quickly here. You can see, first of all, that I have actually those points. I clicked on them there just to see what their values. I hope you can realize that definitely 1 is greater than those two values of 0.05 and whatnot. Also, if you increase the values of n here up to 100, you will see that this does, it was increasing for a short time, then decreasing forever and ever and ever thereafter. And it looks like it's going to decrease down to 0, and it actually will. It just takes a very long time to get there, but it'll eventually decrease down to a height of 0. So there you go. That's a good visualization of that. Let me hop back over to my laptop. I like that example just because it uses technology. Not that I love using technology for these problems, but it is kind of nice to see how you can use technology to help you with visualizations. So that is all the material that we need from sequences to be successful for chapter 11. The big heavy hitters in this section would be, let me go through and just find them just as a brief recap. It'd be great if we had that time to do that every single time. Let me go through and find the heavy hitters here. Okay, one of the heavy hitters. If your limit of your sequence as n goes to infinity exists and is finite, then we say the sequence converges. Very, very important. Super important. So if you're keeping notes on what are hugely important, page 3. There you go. Otherwise, we say it's diverges. So, and then, yeah, very important. Although you get so used to this theorem that you forget that it's an actual theorem. But if I hand you a sequence, you can trade it out for its function to determine if the function converges. If the function does converge, then the sequence converges to the same value. Remember the warning. The converse is not true. So if your sequence converges, it does not mean the related function will converge. Luckily, you will never even wonder that question. It's not going to be an issue, so you don't have to worry about that. But page 4, very important. Page 5 is peripherally important because it's just the limit laws, but you should know that. And obviously page 6, important because the squeeze theorem, but again, you should know that. Squeeze theorem is pretty awesome. Here's the oddball. Page 7, this theorem is or can be incredibly powerful in very unique situations. So if you're ever dealing with a sequence and your sequence is just popping between negative and positive values, and you're like, the fact that's popping between negative and positive values is killing me. I want to just look at the positive values. Well, guess what? That's what this theorem allows you to do. If you know that the sequence pops between, actually, let me give you an example. I just thought of one. as I was talking. So for example, in this case, if your sequence was, let's say, -1 over 2 to the nth power. Well, there's a problem with trading this out for a function. It's just a massive problem with trading this out for a function, because if you try to trade this out for f of x is equal to a -1/2 to the x, again, x is a continuous variable, so it could be a half. And if it's a half, you're taking the square root of a negative number. But what this theorem tells you is that, man, if you think this converges, take a look at its absolute value. If the absolute value converges to 0, then the sequence itself will converge to 0. And so if I go back and say, you know what, I can't take a look at the function version of this sequence because I could possibly be taking the square root of negative. You can say, well, no, actually, let's instead look at the absolute value of our sequence, which will actually just be a 1/2 to the n. And then I can say, great, if I want to look at what the behavior of that is as n goes to infinity, I will trade it out for its function. And as x goes to infinity, you can just do this using Calc 1 techniques. As x goes to infinity, this will tend to 0. It's just 1 over 2 to the x. That's 1 over infinity, tends to 0. And thus, that implies the limit as n tends to infinity of the absolute value of a sub n is 0, because that's what we just compared to. And via that theorem tells us the limit as n goes to infinity of a sub n itself must be 0. So not often, actually, I shouldn't say that. I should say every once in a while, it is useful to get rid of those negative signs. This theorem only works. Where is it? There it is. It only works if the limit is 0. So that's kind of important there, is that if you trade it out for a function and the limit's 5 or something like that, you can't use this theorem. So just be very aware of that. It won't creep in a lot. This I actually just used. That is a very important theorem, so I guess they're all sort of important. And then we went into a round of examples. So all these were just the examples we went through. Each one of those examples I handpicked for a specific reason, like this guy right here involving factorials. Very important to play with factorials, because we will, by the end of this chapter, be all over factorials. Yeah, and then I use L'Hopital's quite a bit just to remind you of that. Because I know that can be easily forgotten. I tried indeterminate forms quite a bit for you guys. And then we deal with bounding. Now, to be honest with you, the bounding of sequences doesn't happen often. So unfortunately, there's a little sad trombone slide, womp womp, right here, because you spent a little bit of time in lecture learning about bounding sequences, and having monotonically increasing bounded sequence means that your sequence converges, stuff like that. However, turns out you're not going to use that a lot. It's used in theory, but not in application. So it's kind of unfortunate that we don't get to touch upon that other than just what we did right there. All right. So that rounds out section 11.1.